Hey, welcome back to Chem 121. Today what we're going to talk about is polarity. And one of the things that we need to discuss is earlier we were talking about different types of molecules. So, for example, we had magnesium bonded to chlorine. What we need to know about that is this relationship between the magnesium and chlorine and where those electrons hang out closest to. And one of the measures for really who has the greatest attraction for a bonding pair of electrons is the electronegativity. So electronegativity is defined as the attraction for bonding pairs of electrons. And so if we look at magnesium and chlorine, what's going to happen is those electrons, chlorine has a higher electronegativity, and we're going to look at those values in just a moment. But what that means is the electrons between magnesium and chlorine are going to tend to migrate towards the chlorine. They're going to hang out a lot closer to the chlorine, so they won't be right in the middle. What that does for us is that actually makes this chlorine slightly negative, and in this particular case it isn't really slightly negative, it actually makes this negative. And the same thing with this chlorine over here. So it creates a situation where magnesium becomes positive too. Now, if we look at something like water though, water actually, the electrons are going to tend to move towards move away from the hydrogen. They're going to move towards the oxygen, and so we get this because oxygen has a higher electronegativity than hydrogen. The electrons move up, and instead of being totally negative or totally positive, they only become slightly negative, and these hydrogen becomes slightly positive. And that little funky letter that I'm drawing there is actually a small case delta. And so what we have is it kind of looks like a little candy kiss. So we have a positive on the bottom, we have a negative on top. Now, what that does for us is it creates what we call polar bonds. So if we look at the bond between hydrogen and oxygen, we have this negative charged end, or slightly negatively charged end, and a slightly positively charged end. So you kind of have a magnet that's created between those two things because of their different charges. Now, because you have polar bonds does not mean that you have a polar molecule all the time. If you have a molecule that's the same all the way around on all sides without electrons pushing them away, you may end up with a molecule with polar bonds, but not a polar molecule. And so we're going to look at that in the next couple slides of what determines whether it's a polar molecule or just polar bonds. Okay, looking at electronegativities really quickly, you'll notice that this chart, hydrogen has an electronegativity of 2.1 and the oxygen has an electronegativity of 3.5. And so if we're just bonding these two together, and we're not worrying about the other hydrogen that's there, this is our 2.1 and this is 3.5. So what that tells us is the one with the greater amount of attraction. And so we get this movement of electrons towards that oxygen. If you look in the periodic table, the one with the lowest electronegativity is this francium down here in the bottom of 0.7, and the one with the highest or the greatest attraction for bonding electrons would be fluorine. And so across the periodic table, we have a tendency to increase as we move from bottom left to top right. You'll notice that chlorine is 3.0, nitrogen is 3.0. So this upper corner has the greatest electronegativity, or the greatest attraction for those bonding electrons. Now, when we look at magnesium, we have this magnesium and chlorine. Chlorine's got an electronegativity of 3, and magnesium has an electronegativity of 1.2. What they've defined is it's kind of a scale of electronegativity difference. And so if we take that 3 minus that 1.2, we get a 1.8. And so what they're saying is that anything that is greater than 1.7 is going to create actually a polar bond. In other words, chlorine is actually going to take those electrons, hang on to them, and leave the magnesium with a +2 charge, chlorine with a -1. So anything greater than 1.7 is going to give us what we call ionic. Now, if we have something less than 1.7, we're going to be a polar bond. And so if we look at this nitrogen, this NH3, you'll notice I didn't put the extra pair of electrons on top, but we'll draw this again. Nitrogen has a pair of electrons, hydrogen, hydrogen, hydrogen. And I drew this like our molecule earlier. It's trigonal pyramidal. So this nitrogen kind of stands up in the air above all those hydrogen. And if you look at this, we have 3 for nitrogen, and we have this 2.1. So the electrons are tending to move towards the nitrogen, making the nitrogen slightly negative. So we put a slightly negative up there, or a delta negative. And these guys are all slightly positive. Now, each one of those bonds is polar. Now, this particular molecule, the way I always think about dividing this up to see if it's a polar molecule or not is there a location I can put an equator through this molecule that makes one end positive and one end negative? And because that nitrogen kind of stands up above all those hydrogen, I always think I can draw a line there. This whole side up on this end is slightly negative. This whole side down on the bottom is slightly positive, and we get this polar molecule. And what they call is the dipole moment. The dipole moment is actually in that direction. In other words, the general direction that the electrons are moving is up towards that nitrogen. If we look at water, water looks like this again. You'll notice you guys will get used to water being bent. Again, this is, I think we saw was 3.5. This is 2.1. And so we have those electrons moving up towards oxygen. Water can be divided just below the oxygen. And you notice the dipole moment is in this direction. So we have this nice polar molecule. And so we're going to look at some of what happens because of that polarity now. We get these what are called intermolecular forces, and these intermolecular forces we'll talk about in just a moment.